Hello everyone, in this video I'm going to talk about hash tables and the way to use hash tables to implement a hash set or a set data type and also a map data type. More specifically, I will create a hash set first and then a hash set of strings in C programming language. And then after that, I will create a hash map mapping a string keys or char star keys to integer values. And for both set and map, I use the same hash function. I use a similar hash table. And I will use a linked list to resolve any collision that may happen in my hash table. So the implementation for the set and map would be very similar. Let's begin by looking at my header file. I have a hash.h file, which is my header file. I have included math.h because I will use square root later, stdio for printf, stdlib for malloc, string.h for multiple string functions that I use, ctype.h for is a space or other. Actually, that's the only one for is a space function. And also I have defined a constant called bins. That's the initial number of bins that I have for my hash table. There's a reason behind 101 because 101 is a prime number. It's a good choice for the number of bins. Without me explaining why the number of bins for a hash table should be a prime number, you can accept it for now, but there's a number theory reason behind this. Anyways, after these definitions and includes, let's look at the node of the linked list that I create in every bin of my hash table. So before I continue talking about the node of a linked list inside my hash table, let me tell you how my hash table looks like. For both hash set and hash map that I'm going to create, I use the following table. It's a table made of bins number of nodes. In the case of hash set, I call the node. In the case of the hash map, I call it map node. But as I said, they're similar, concepts. And I call this a table. As you see, my hash table has a table and the table type is node double star. I'm going to focus on hash set and explain all the data types in a hash set, and then we can extend it to a hash map. So the table type is node double star. Why? Because it's an array of originally size 101 node stars. Each single one of these nodes is a node star, or each of these elements is a node star. We have node star here, node star here, node star here, and the index would be 0, 1, 2, all the way to 100. But that's not going to be a constant. The length of this table, the number of elements in this table can grow if you add more than 100 elements in this hash table. So originally, all of these refer to null because they all should represent empty linked lists. But After adding multiple elements, maybe this linked list is made of, let's say, 2 nodes, and after that it points to null. Maybe this one points to only 1 node, and this points to null. Maybe there is an empty bin that points to null and has no element in it. Maybe the last one has, for example, 3 elements in it. It's very possible that, you know, each bin has different number of values in it. Later, I will show you in the insert function that when you want to insert a value, in this case, because I'm designing a set of strings, set of char stars, my values are all char stars. When I insert a char star, I first need to call a hash function, which I'll show you later, on it to get a value between 0 and 100. And that value becomes the index for this table. And then after I find the hash value of the given string, I can, find out which of these bins should host the value, and then I'll insert the value. But before inserting a value to a hash table, you're going to make sure that your table does not have the same value, because a hash table can implement a set abstract data type, and a set does not accept duplicate values. Just like binary search tree. The binary search tree is just like a hash table that doesn't accept duplicates. So if there's a duplicate and you want to insert a duplicate value, basically the insert wouldn't be successful, and we're gonna abort the insert operation. Now, let me erase all of these annotations and go forward with the code. So in the code, as I said before, we need to define a node for the linked list of our hash table. As you see, in each node, we have a struct node star next. That's basically a simple linked list node. And then there's a char star value, because I'm going to store string values. And I will type the struct node to node. And also, after I define that node, I will create another structure. I call it hash set. That's made of a list of bins. As I told you, it's a list of, it's an array of node stars. So the type of table would be node double star. And then there's an int size, which is initialized to 0, and bins, which is initialized to 101. That's the number of bins. And then, size will increase when you add more values, and number of bins remains constant unless you want to rehash and grow the size of your hash table. I'll talk about map node later. That's for map, for the hash map implementation. But hash map also is for map implementation, but I don't want to switch between set and map. I'm going to first finish the implementation of a hash set. Then the hash set implements a search operation, which looks for a given a string in a hash set, and also it implements the insert operation. Let me open the hash set.c and explain how insert and search look like. Before doing that, in order to initialize a hash set, an empty hash set, what I need to have is a constructor. This is my constructor, which is called setInit, which initializes a set and returns it. In order to make this function, I need to first define a hash set. The hash set, as you remember, was a structure made of a table. This is how I initialize my table. It's node double star, malloc, bins, and then size of node star, where node was the node of a linked list, as I showed you before. Size is initialized to 0, number of bins is equals to bins, which is 101. Then in a for loop, I go over all the bins and I set them equal to an empty linked list. This is an empty linked list. When you set the head to null, that means you have an empty linked list. And I return the hash set. So after initializing the hash set, it's time to show you the hash function for the hash set. The hash function gets a char star and number of bins, and basically returns an index or an integer value from 0 to the number of bins minus 1 based on the content of this string. Now, let's say the key is a string like hello, right? So, or let's make it even simpler. Let's say key is ABCD. And I'm sure you know what how ABCD is stored in memory. Basically, it's a sequence of ASCII codes. ASCII code of A is 97, ASCII code of B is 98, ASCII code of C is 99, and ASCII code of D is 100. And then finally, we have a 0 at the end of the string. So in order to create a hash value for this string, I'm going to combine these ASCII codes, not in a simple way, not by adding them, by applying a formula on them so that the return value of that hash function gives me a relatively random value that is uniformly distributed between 0 and number of bins minus 1. So there are many ways to do this. The most common way to find or to calculate the hash value of a given string is using this for loop. This for loop basically multiplies each of these ASCII codes by a power of a prime number. In this case, my prime number is 31, and then it adds them all together. So this for loop eventually will calculate the following value for ABCD: 97 times 31 cubed plus 98 times 31 squared plus 99 times 31 plus 100. It's not very easy to see how this is going to generate this polynomial, value. This is kind of like a polynomial function where x is set to the prime number 31. But if you do a little bit of a study and if you try to traverse the flow of this for loop, you will realize that this is going to generate what I wrote here. And after you combine all the ASCII code in a weird looking way, you basically find the mods of bins. The mod bins means you divide by the number of bins and find the remainder. That's going to give you always a number between 0 and number of bins minus 1. So that will return always a number between 0, I should say an index. The index from 0 all the way to bins minus 1. The reason I will say this is an index is because we'll treat it like an index for this table. And you may say, what about negative numbers? Because this for loop is going to calculate a very long and heavy mathematical operation. It may overflow and may give you a negative number, but we eliminated the chance of the hash value become negative by defining it as an unsigned number. So this small function has lots of details in it, which I tried to explain most of it in this short video. And then after defining this hash function, it's time to show you the insert and search operation. What I'm going to do is I'm going to show you the search operation first, because I will use search inside the insert. The search gets a hash set by value and gets a val, which is a char star, and tries to locate the val inside the hash set. If it can find the val, then it returns 1, otherwise it returns 0. That's why the search returns an integer. So first, we use a hash function to calculate the index. And then after you got the index, you will say this. Either this value does not exist in this hash set, or if it exists, it's going to be in a bin whose index is given here. So all I need to do is I need to have a linear search in my linked list whose head is given as h.table index. So basically, I will define an iterator in my linked list and I initialize it to the head of the linked list. As long as the iterator is not pointing to null, I will say iterator equals iterator arrow next. And, if I find it, that means if iterator arrow value equals val, then I will return 1. Otherwise, I will return 0. That's the search operation. Then after you take care of the search, it's time to do the insert operation. The insert operation is very simple. You want to insert a given value into a given hash set, but the difference between insert and search is for insert, we're going to pass the hash set by reference because insert may change the state of the hash set H. So we're going to pass it by reference so we can change the state of H if needed. So it also returns an integer. That integer shows whether or not the insert is successful. If the value already exists in the hash set H, we need to return 0. Otherwise, we need to return 1 after inserting the value into the hash set H. So in order to insert, we start by finding the index of the value in the given hash set. After the index is calculated, you don't even need to calculate index before. You can do it afterward. It's better to first search. Let's search for the value in a given hash. If you find it, that means the value is duplicate, so return 0. That means my insert operation failed prematurely because I was trying to insert a duplicate value. But otherwise, we're going to do this. We first calculate the index. That index will be the index of the linked list that I'm supposed to insert a value to. Before I insert, I'm going to make sure my hash table is not overloaded. We define a load factor for every hash set or a hash table in the following way. The size of the hash table, which is the number of elements that is already inside the hash table, over the number of bins is called the load factor. If the load factor is greater than or equal to 100%, we want to rehash. The rehash basically grows the number of bins by a factor of 2 or more. That means it at least doubles the number of bins, and then it migrates data from the old hash table with a smaller size to the bigger hash table with bigger size, to the new hash table with a bigger size. So let's say you may or may not rehash, depends on how many elements already are in your hash table and how many bins you have. If we rehash, or if we don't rehash, it doesn't matter. After line 19 and 20, we come to line 21. That's when you want to insert the new element containing the new value. So first, we allocate enough space for that node that we're going to insert. Then we're going to set its next element equal to the current head of a linked list that is at index. That means the new element is going to be injected at the very beginning of the linked list. So it's going to become the new head of the linked list. So its next is going to become equal to the old head of the linked list. Then its value is going to be the duplicate of the value that is passed to the insert function. Then we're going to set the head of the current linked list equal to the new element. We're going to increment the size of the whole hash table or hash set, I should say. and we return one. One means it was a successful insert because it wasn't duplicate. So that's pretty much most of it, most of the implementation for my hash set. The last thing I wanted to say is the rehash operation. Let me briefly talk about it. The rehash is implemented here. It's a very simple function. It gets a hash set by reference, and it's going to increase the size of the hash set by at least doubling the number of bins. So let's first store the old table into a old age table into an old table variable. Then let's store the old number of bins. Then let's create a new table. To do that, we need to first allocate enough space for it. The size of the new table would be 2 times number of the bins, number of old bins. But that may not be prime. As I told you before, it's better to keep the number of bins prime. So I will call the next prime, which I implemented as well. That's going to give me the next prime number that is greater than or equal to 2 times number of bins. And I'll show you the implementation after this. So after you call this, you get a prime number that is at least twice the number of old bins, and then you create a table of this size, and then you set the size equal to 0. Number of bins would be the same number, the next prime after 2 times number of bins, and then in a for loop, as you see here, I will migrate data from the old table into the new table. How do I move data from old to the new table? As you see here, I will do the insert operation into the new hash table. And that's how the data is migrated. I go over all the bins of the old table, and for every node in the linked list of bin number I of the old table, I move it to I move its value to the new table. So that's how the rehash works. And finally, next prime is a function that I implemented in a brute force fashion. There is a much better implementation, but it requires you to know some primality tests. I try to make it simple. So let's say you want to get the next prime after min. Let's have an infinite while loop, and let's define the flag called prime. It's initialized to 1. Then in a for loop, I start dividing my next candidate, which starts on min, and in each iteration it increases by 1. I try to divide that candidate by a number from 2 to its square root and see if it's divisible. If my candidates for prime number mod the divisor, which is a number from 2 to the square root of my candidate, is equal to 0, that means my candidate is divisible by a divisor, therefore it cannot be prime. So I set the prime to 0 and I break. After I break from this for loop, I will check if the prime flag is 1. If it's 1, I return min. Otherwise, we can't return min yet. We need to increment the min, which is my candidate for a prime number, and then try again. This while loop continues until we find some prime number. So that's pretty much my hash set. Let me show you a quick test for my hash set. I have created this test. I first initialize my hash set. Then I have created an array of fruit names. As you see, I have added apple, orange, banana, cherry, kiwi, orange, banana, and pineapple. So I intentionally have repeated these 2 fruits. and then just to see whether my hash set can remove these duplicates and store them all in my hash table. So this step is the initialization step. Then I will have a for loop, and for all the 8 elements in this names array, I will insert data string into my hash set, and then I will iterate through the bins of my hash table, and I will iterate through every single node of the linked list of that bin, and I will print the value stored in it. And let's run it to see if this works properly. So let's bring my Ocelot. Let's ls. As you see, I have a hash.h, hash map.c, hash set.c, and then tally.c. So first thing I will do is, I haven't shown you the hashmap.c. I'm going to start with hash set.c. I'm going to first compile it. To compile it, I will do this gcc-o hash set example hash set.c -i.-lm. The reason I use lm is because I have a sqrt function in the math.h, so I need to have a -lm. Let's press enter. That's going to compile my hash set, and it generates an executable called hash set example. Let's run it. I guess, yeah, I guess I made a mistake. This is hash set. All right. And as you see, it prints only 6 of the fruit names. The ones that are duplicate are eliminated. Only I have apple, cherry, kiwi, banana, orange, and pineapple. One obvious difference that you see between the hash set and a binary search tree is that when you have a hash set, the order of elements is not going to be preserved. So the fruits are not going to be printed. I'm sorry, the order of the elements are not going to be sorted in a hash table, or in a hash set, but in a binary search tree, we do have a sorted order, right? And obviously, the order is not going to be also the same order that you insert the elements. So the hash table or the hash set is completely gives you random order of elements. It's not going to be alphabetically sorted. It's not going to like a binary search tree, or it's not going to be in the order that they are inserted like a normal array. So don't use a hash set if you care about the order. All right. Given that observation, or by explaining that observation, I'm going to move toward my implementation for a hash map. A hash map is basically it's very similar to the hash sets that I showed you. Basically, I have a table which is an array of linked lists. The only difference between hash map and hash set is the way the node of each linked list looks like. Let me go to the hash.h to show you the node of a linked list in my hash map. The node of a linked list in my hash map looks like this. It basically has the next reference. It has a key, which is a char star, and it has value, which is an int, because I want to create a mapping between the strings and integers. And I will use this later to tally or to count the number of words, the number of occurrences of certain keywords in a given input. So a hash table is just like a dictionary in Python, where you can either tally the vote or count how many occurrences of like a certain keywords can be found in a given corpus or a textual document, so on and so forth. So this is basically an equivalent data structure to dictionaries or hash maps in Java. Dictionaries are in Python, hash maps are in Java. Okay, so this is my structure map node. As I said, that's the basic difference between a hash map and a hash set. And whenever I want to define my hash map, I make sure that the table should be a map node double star, not a simple node double star, because this is a hash map, not a hash set. But it has the size, it has the bins. This is very similar. And the two main functions that a hash map needs to have is not going to be search and insert anymore. I will have a get and a put. For those of you who are familiar with hash map in Java, you know what get and put means. Get basically gets a key, which is a char star, and returns the value corresponding to that key. Of course, because C is not object-oriented, I have to pass the hash map by value as the first parameter of the get. But if you remember the hash map .get method in Java, it only gets one key, not any second input parameter, like in this case. Because Java is object-oriented, but C is not object-oriented. So the next one is put, which gets a hash map by reference because it's going to change it. It's going to get the key and a value, which are basically strings and integers. And put will return an integer. That integer would be either the old value corresponding to the key, or it's going to be 0 if the key didn't exist before calling the put. Basically, put will create a mapping between this key and this value. If the key doesn't exist already in the hash map, we're going to insert a new node to one of the linked lists that are preserved in the hash table. If that key already exists, we're going to return the old value, and we're going to set the value corresponding to that key equal to the third parameter here. And I have a hash init function which initializes my hash map. So let's get to the hash map.c. Also, one more thing I forgot to mention is that I have a contains key method or function, I should say, for my hash map that gets the hash map and a key, and it checks whether that key exists in this map or not. If it exists, it returns 1, otherwise it returns 0. So let's get into the hash map.c function, look at the constructor first. It basically creates a table of size bins, but the only difference between hash init and set init is that here we create map node double star for the table. Over there, we had a regular node double star. And then we initialize all the linked lists to empty, to null. And then this returns the hash map. The hash function is exactly the same as the hash function I showed you in hashset.c. That's going to get a char star key and a bins and the number of bins, and it's going to return the index of the bin that we should store this key. It has the rehash, very similar to the rehash operation that I showed you in the hashset.c. The contains key basically looks for this key in this hash map. First, we call the hash function on the key and the number of bins to find out the index. Then we're going to look for the key in the linked list that is stored in the index. So this for loop is going to linearly search for that key. If it finds that, it's going to return 1. Otherwise, we're going to return 0. Then we have the put operation. In the put operation, first I will call the hash function to get the index. Then I will traverse the linked list of that index in a linear fashion and try to look for the key. If I find it, I will store the old value in a variable called oldVal. Then I will update the value corresponding to that key to the value that is given as the third parameter. Then I will return the old value. That's when you have the key already in your hash table. If you don't have it, then you're going to insert a new one. So you're going to increase the size. Before you increase the size, make sure the size is not going to exceed the number of bins. Otherwise, the load factor will be greater than 100%. So if that's the case, rehash and increase the number of bins. After that, you're going to create a new element. But this element is going to be of type map node because this is a hash map. Then set the next value equal to the original head of the linked list. The key is going to be the duplication of the key that is passed. The value will be the value that is passed to this function as the third parameter. Then we update the head of the linked list stored at index. And then increase the size and we return 0. Why we return 0? Because there's no old value corresponding to this key. Therefore, we're going to assume the old value was 0, because normally in like hash tables are used for tallying the votes or like counting the number of occurrences. So the default value is better to be 0. The get is much simpler. It just gets a hash map and a key, and all it does is find the index, do a linear search on that on the linked list stored in that index. If it finds the key, it's going to return the value corresponding to the key. Otherwise, if it cannot find it anywhere, it's going to return 0. Again, we're going to assume that if the key doesn't exist, it is corresponding to 0, because normally, hash maps are used for counting the occurrences of something. So the default value should be 0. And then I have a toString method or toString function that constructs a string representation of my hash map. This is going to go over all the bins and all the nodes inside the linked lists of each bin, and it's going to append those elements to my return value, and eventually I return the return value, which is a string representation of the hash map. The next prime and rehash are just similar to the hash set. So after we created this hash map, I'm going to show you an example of how to use it. My example is called tally. Basically, what it does is gets a bunch of keywords using command and arguments. Those keywords are going to be stored in my hash table using the put function. We're going to initially correspond them all to 0, and then we're going to read a bunch of words from input, and if each word, if the given words from input can be found in the hash map, that means it is one of those reserved words. If that's the case, then we're going to increase the frequency of that word by 1, because this program basically looks for keywords, certain keywords that are given in command line arguments, and is going to, whenever it finds a new occurrence of it in the standard input, it's going to increase the frequency. So get function gets the old count or old frequency plus 1 becomes a new frequency. Then we use put to update the frequency of that word. Eventually we're going to print out that hash map that's going to print out the number of occurrences of every single keyword that you're interested to find out. So let me run it, and you see how it works. So to do this, first we need to compile. I've already compiled it. GCC-O tally, that's the name of my program. Tally.c hashmap.c-i.-lm. -lm is used because I used sqrt inside its prime function. So if I compile it, it compiles it successfully. Now let's run it. To run it, I have already done an execution before, so let me read it for you. The executable name is called tally. and I'm interested in finding the keywords or the count of the keywords break, continue, for, while, switch, case, int, char, void, static, unsigned. As you see, these are some of the reserved words in C programming language. And my input is not going to be from standard input. I use the less than operation to redirect the input. Okay, redirecting the input means after you do this, whenever I try to get a word, I don't get it from a standard input. I get it from this hashmap.c file. And because hashmap.c contains a bunch of C code or C lines, it is very likely that we get some positive values for any of these reserve words, because a programming language, a program written in C has a lot of occurrences of the reserve words. Let me show you one more time the function that gets a single word from input. This function basically calls the getChar multiple times. If you remember, getChar is going to receive data from standard input, which is the keyword. But after I redirected using the less than, this operation is going to redirect the input, and I'm not going to receive data from standard input anymore. I will read the hashmap.c file. And also, one very important point to remember is that when you redirect the input this way, that's not going to be considered as one of the command line arguments. So again, let's go back. When I wanted to go over all the command line arguments and include them in the in my hash map, none of these argv's are going to be equal to this last two pieces, which are less than hashmap.c. So that's not going to be part of my argv array. So let's run this and figure out how things will look like. As you see, it counts how many breaks I have, 0, how many unsigned I have, 1, how many switches I have, how many cases I have. Char is 2, void is 2, for is 9, static is 4, continue is 0, int is 13, while is 1. You may say, oh, we had too many chars. That's correct, but the chars were not chars, they were char stars. So I can show you another execution of it, and this time include char star as well. Let's see, 1 second. I guess, let me see. All right, yes. So as you see here, I had to put char star in double quotations, and it gives me 3, right? So I have 3 occurrences of char star, while I had 2 occurrences of char. So overall, char would be 5 occurrences. And you can verify that by looking at the hashmap.c, which I, make it available. You can see it. Yeah, I mean, you see we have so many whiles and for loops and all of that. So let's do one last thing. I showed you how to redirect the input. Is it possible to redirect the output and write these in a output file? The answer is yes. Is it possible I can say, let's write the output into a file called results.txt, and it does it. That's why you don't see then the counts on the output on the console. So in order to show you the result, I just need to say cat result.txt, and it basically shows me the same count, right? So that's pretty much all I wanted to say about basically hash sets, hash tables, and also redirecting input and output. Thank you.